All right, good morning. We are going to launch into lesson 4, which is kind of extending our trig identities um, units. I don't know if I'd call it a unit, but our focus right now to identities that are derived out of the Pythagorean theorem, but they're derived out of the Pythagorean theorem in kind of a different way than what you might think, and it kind of all comes back to our basic functions, and then it also kind of leading into the unit circle a little bit. And unit circle, if you're kind of like, what, unit circle? Don't worry about it. That's not integral to this. Um, but for those of you who do know what it is, these you can find these from that. We won't do that, but they can be found. So let's just kind of dive in. We're going to look at our three main identities that we're going to use today. The way you can kind of recognize most of these is they have squares in them, right? They're not like the ones we did yesterday, where it was just kind of like, oh, well, we remember that sine is 1 over cosecants, and all of that. We instead we're looking at things that are derived kind of more out of a formula. So let's get started. All right, so here is a triangle. Instead of labeling it, side A, side B, side C, we use the terminology we use for our trig functions. So assuming that this is my angle right here, that would make this my opposite leg, my adjacent leg, and my hypotenuse. And from that, and a bunch of wrangling around, they came up with this main Pythagorean identity, which is this one right here. So the one on the left is the big one. And if you look at it, it should kind of intuitively make some sense to you because, cosine and sine are kind of like, the values that you get when you go around a circle, right? And we were looking for all those different values, like, oh, what's the value of this at blah blah, right? And they were kind of listed as coordinate pairs, right? So if you have something that's listed as a coordinate pair, and your cosine value is here and your sine value is here, well, it kind of makes sense that for x and y squared to equal your hypotenuse squared, then that becomes your cosine value and your sine value. So that's kind of a real light explanation of why this works and why we use that. And the one just basically represents your hypotenuse, which in the case of a unit circle is your radius, right? So let's just take this now. And so what we need to be able to do with these identities in order for them to be useful to us is we have to be flexible with them. All right, we have to be flexible with them. So the first thing we got to talk about is what is the fact that we can rearrange these any way we need to. And we're just looking at this one right now. I know these two are here, but we're going to just focus on this one. So let's say that I saw something that was just cosine squared. Well, the thing is, can you take this expression or this equation and solve for cosine squared theta? And the answer is yes, you can. So if you wanted to do that, you would say, okay, if I have cosine squared theta plus sine squared theta equals 1, and I want to solve for cosine squared theta, I would just get rid of the sine squared theta by subtracting it from both sides, right? And then you would solve for your cosine squared theta, and you would have 1 minus sine squared theta, which is, and you don't have to do anything else beyond that. We're not asking you to find cosine. We're just saying find cosine squared theta. And similarly, if I had something where they just listed the sine squared theta, right, you start from the same starting point, right? And then instead of moving the sine squared over, you would move your cosine squared over this time, right? And so they look really similar, which is kind of nice because they're easy to recognize. There's a one in there, and then there's a square term. So we have to be able to kind of get flexible with this and recognize that most of the time they're not going to say, oh, cosine squared plus sine squared equals 1, and that's going to just be in there like that. We're going to have to usually solve for one or the other. And so if you can kind of remember that one is equal to the other when it's subtracted from, like, one of the functions squared is equal to the other function being subtracted from 1. That's kind of, that should help you. All right. Now, these other ones over here are kind of weird, right? I'm not going to lie, but I'm going to show you where they come from, so you'll be kind of like, oh, that makes sense. All right. So what we're going to do is we're going to start with our cosine squared plus sine squared equals 1. Again, we're going to start with that. All right. Having established that this is a thing, right? And so what we're going to do now is we're going to take this and we are going to divide the entire equation by cosine squared. All right. So I'm just doing that to see what happens here. All right. So we're going to divide this, this, and this all by cosine squared theta. Right. So, and I can do that. Right. We can do whatever we want to an equation as long as we do it to both sides. So cosine squared divided by cosine squared is 1. And then before you try to like get too tripped up on this, remember that when they're both squared, that's the same thing as sine theta, cosine theta, and then another sine theta, cosine theta. And then we know what sine theta over cosine theta is. This is a tangent, right? This is tangent theta, and we have another one. So this, if you multiply these together, you have tangent squared, right? So this becomes tangent squared theta. And then 1 over cosine squared can also be kind of decomposed into 2 of them, right? Like this. And 1 over cosine is secant, right? So you get 2 of those, and the same thing over here. So you get secant squared. And the way you can remember that tangent and secant go together is tangent has a cosine in the bottom, and secant has a cosine in the bottom. So their denominators, I should use the proper math terminology here, their denominators are identical to each other. They both have cosine in their denominators. So because of that, they pair up, right? And so we're going to do the same thing now with this starting equation, with our Pythagorean equation, and instead of dividing through by cosine, we're going to divide through by sine squared, right? So we're going to go sine squared, and then sine squared. And you're going to see, now we can go a little faster with this one, that it's going to do the same thing, right? One cosine over sine is cotangent, right? So cosine over sine theta equals cotangent theta. So we have 2 of those. So you're going to get cotangent squared theta. This turns into 1, and then 1 over sine is cosecant, and we have 2 of them. So we're going to have cosecant squared. All right. And so these are how you arrive at both of these. And again, this one you can remember because cotangent and cosecant both have sine in the denominator. So that is where all 3 of these identities kind of come from, how they work together. And again, with these just the same as the first equation, our original Pythagorean, we will need to be flexible with this to be able to kind of move things around so that we could swap, the tangent and the secant if we had some negatives or things going on. You won't have to do a lot of that, but occasionally they'll try to trip you up. So it's just good to remember that you can move things around in any kind of algebraic equation, even when it involves trig functions like this and squared trig functions. And these look really scary, but we're not asking you to evaluate them or anything. We're just saying just kind of remember where this comes from and that you can move these things around and kind of substitute them for each other. And if you have that kind of sort of like Lego building mentality with this, I think you'll find this kind of interesting. So that's this kind of long introduction video, but now we've gotten this out of the way, and in the next videos we can solve some of these things. All right, so we'll see you